Okay, today we're going to talk about the second fundamental theorem of calculus, but let's rewind for a minute and make sure we know what the first fundamental theorem of calculus is. And that was if we integrate a derivative, you get back to the original. Right? The first time we wrote it, you were like, well, yeah, like the antiderivative of the derivative is back to the original. Now, we do need to be careful because that's either with the plus c or with the limits, depending on if the problem has limits or not. So there is sort of two pieces to think about there. Let's write it out one more time. Actually, why don't you answer that question? Fill in the right-hand side of that equation. The integral from a to b of f prime of x dx is... And yes, you were right to say it's definitely f, like the antiderivative of the derivative. I'm definitely back to f. And then I'm just thinking, do I have limits? If so, top minus bottom. If there weren't limits, then we would just put a plus c on the end. That's the first fundamental theorem of calculus. And we said this already, but just a reminder, and we'll put it formally in the notes here. The ways to evaluate that. There are three ways to evaluate that. And there are, there's only two popsicle sticks left. I'll pick a different one then. Area under the curve would have to be a rigged problem to work. Calculator will always work, right? Just let the calculator handle it. Antiderivative by hand, well, do you know the antiderivative of whatever's in there? If you do, then you can do this way. If you don't, then you'd have to use a calculator. All right, all of that is first fundamental theorem of calculus stuff that hopefully we already know. Second fundamental theorem of calculus. So the first one is if we integrate a derivative. The second one is the reverse. If we derivative of an integral. What do you think happens if we take the derivative of an integral? If we integrate a derivative, we're back to the original. If we take the derivative of an integral, we're also back to the original. Like, those undo each other. It's like one of the rules is squaring a square root, and the other rule is square rooting a square. It's like it's kind of the same thing, right? Although you do have to be careful with that one because the plus minus thing, and there's something to be careful with here, and that is we have to be careful about the chain rule. So the first fundamental theorem, you got to be careful with the limits, plus c or not plus c. With the second fundamental theorem, you have to be careful with the chain rule. So let's set it up. d dx, the integral from a to u. And by the way, where u is, a is a constant, and u could be some function of x, of f of t dt. Got all kinds of variables flying around in here. Let's see. Let's do the antiderivative first. The antiderivative of f, of little f, well, sort of the hint for the answer. So what's the antiderivative of little f? Big F. If we're working backwards, the antiderivative of little f is big F. So big F, and then plug in the top one minus plug in the bottom one. Kind of going the long way around here to prove a point. Now let's take the derivative of both of those pieces. What's the derivative of capital F? Lowercase f. But here's where the chain rule comes in. We have to be careful about what's on the inside there. So du dx. That's our chain rule issue right there. What about the derivative of f of a? It's easier than this one. A is a constant. So if I evaluate whatever the function is at some number, I get a number, and then I take the derivative of that number, and we get 0. So the short answer is, or the short, let's just rewrite it. The derivative of the integral from a to u f of t dt is f of u du dx. So all you do is plug in the top one, but also chain rule off the top. So the derivative of the integral gets you back to the original, but you have to be careful with the chain rule. So that looks really complicated. In practice, it's pretty easy. So let's find the derivative of the integral from 5 to 3x squared of t sine of t dt. I have to put that where you can read it. That helps. Now, people who don't know the second fundamental theorem of calculus are going to try to work from the inside out like you normally do, and they're going to be stuck because they don't know how to take that integral. But people who are paying attention are thinking, wait a minute, the derivative of the integral, that just cancels each other out. And all I'll have to do is plug in that top limit wherever t is. So 3x squared times the sine of 3x squared times chain rule (6x). And then we maybe clean that up a little bit. 18x cubed sine of 3x squared.
Did you just take the derivative of the top one as well?
Yep. So excuse me, the concept is involved, tricky, derivatives, integrals, but in practice, plug in the top one, multiply by the derivative of the top one. That's it. Let me try to reword the problem to be tricky. Find the derivative of h of x equals the integral from x squared to 3 natural log of t cubed dt. That sounds awful, except that you're taking the derivative of an integral. So it might even be helpful to write it like we're used to seeing it. d dx, the integral from x squared to 3 natural log of t cubed dt. Now it looks even better, I think, because you got derivative of antiderivative sitting right next to each other. They should sort of cancel each other out. Okay, but what's different about this one than the previous one? What's that? The top number is not a variable, so it doesn't exactly fit the pattern we want. Is there something we could do to make the top one the variable? Switch them. What price do we have to pay to switch them? A negative sign. So small price to pay. You're right, the x squared seems out of place. So let's switch them. Put a negative sign out front. And take the derivative from 3 to x squared. Natural log of t cubed dt. Now it's set up like we want it to be set up. We should be good. All I have to do, don't forget the negative sign, plug in the x squared. So that would be, careful, x squared cubed. And I guess if you're enjoying safe stop, you can leave that alone. And then the derivative of x squared, which sort of reminds you of the chain rule. Like if you say plug x in for t everywhere, if you put it in right there, that sort of says derivative of x squared. It's one way to think of it. Derivative of x squared would be, let's see, chain rule would be 2x. Whoops. What did I leave off? I left off the natural log. So negative 2x natural log of x to the 6th. Oh, and if we were being multiple choice tricky, we could use a property of logs. Property of logs, anybody? Just to know. What about that exponent? Where can it go? It can go to the front. Like, this is a safe stop, this is a safe stop, but a multiple choice test, or calc chat wanting to be cute, might move that 6 down front. And that would be a place where people would be like, where did calc chat get that from? Like, sorry. Let's do one more. dvx of the integral from sine of x to negative 12 of e to the negative 5t dt. It looks awful because like there's a derivative, there's an integral, there's a sine, there's an e to the power. Like it looks terrible, but you know that derivatives and integrals cancel each other out. So you try that one and then we'll see. How do we feel about that? So get it set up right. Plug in the top one. And don't forget the chain rule. It's pretty easy. I'll pass out the worksheet. Answers are already posted in Schoology. And even though there's only 15 minutes left, you might finish this before you go.